Hello, today we'll be covering complex vector spaces and Dirac notation. And here I drew a bracket in reference to the fact that the Dirac notation vectors are called bra vectors and ket vectors. In the first video, or second video, we talked about basis vectors being in n dimensions. Now basis vectors can be represented as ket vectors, as shown in the figure on the bottom. You'll understand why it's called that later. And any ket vector A can be represented as the sum over a linear combination of its basis sets. And a ket vector can also be represented as a column vector with AI, A2, all the way to AN. And each element of the ket vector is a member of the complex numbers. Now the adjoint of a ket vector or a adjoint is all its components complex conjugated written in a row vector. Now that row vector is something called a bra vector, and now you understand why it's called bra and ket, because they make bracket. And when we multiply a bra vector by a ket vector, you get something that's very similar to a dot product, where you just get sum over all the I equals 1 to n of AI star bi, or in Einstein notation, AI star times bi. Note that if you multiply a bra vector with its corresponding ket vector, you'd get the length of the vector squared. Similarly to the ket vector basis, you can define a bra vector basis. Using the definitions of bra and ket vectors as expanded out under basis, you get bra A times ket B equals over AI star times the bra basis vectors times sum over all j of ket basis vectors times bj. You get sum over all I and j, AI star ij bj. Since the formula we arrived at has to equal sum over all I of AI star bi star, that means bra I times ket j has to equal the Kronecker delta. Since if bra I times ket j equals 1, if I equals j, and otherwise it has to equal 0 in order to make the two formulas consistent with each other. Now I know that bra basis and ket basis is highly abstract, so for a concrete example, a three-dimensional example of a bra basis and a ket basis, bra I will just be the row vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. And the ket basis of I will just be column vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Again, this is just a toy example to make something that's highly abstract more concrete. Since bra I times ket j equals dij, that means the basis set must be orthonormal. Here we will talk about determining the components of bra and ket vectors. Say you have a ket vector A equals sum over all I of the ket basis set times AI. To determine the jth component in the ket basis, you multiply the jth component of the bra basis times A to get A sub j. And similarly, to determine the jth component in a bra basis, you multiply the bra vector A by the jth basis ket vector to get aj star. And notice how bra j times ket A equals bra A times ket j complex conjugated. And note that the ket vector A equals sum over all j of the j ket basis aj equals sum over all j of j ket times j bra times a ket equals sum over all j of j ket times j bra times a ket. And we can do this because of the associativity of matrix products, as each basis vector j and a to draw matrices. So based on this, we sum over all j of j cat times j bra has to equal the identity matrix. Next, we'll talk about bra cat operators, where an operator operating on a cat vector A gives you the cat vector B. And let's define the effect of an operator on a basis I, on a basis cat vector I, where O operated on I equals sum over all j of j cat times OJI. You can multiply both sides of the expression by the cat vector, the bra vector k, to get sum over all j of bra k cat j times OJI, which equals the sum over all j of dkj OJI, which equals OKI. That means the kith component of a matrix representation of operator O is OKI is the cat vector, the bra vector k times the operator operated on the ith basis cat vector. So let the operator C be the effect of first applying operator B on a cat vector and then an operator A on a cat vector. That means Cij has to equal the bra vector I times C operated on the cat vector J. That means I AB J has to equal I times the operator A operated on the effect of operator B on cat vector J, which equals the sum over all k of k b k j equals, and then we could apply the operator to each cat vector k under the sum to get the bra vector I times sum over all k and m of the mth basis cat vector times amk times bkj, which would get you sum over all k and m of I bra times mcat amk bkj, which would give you sum over all k and m of dim amk bkj. Notice how when you sum over all m, everything else goes to 0 except the ith component, which will give you sum over all k of aik times bkj. That means that Cij has to equal sum over all k of aik bkj. And notice that this is the same definition of matrix multiplication. So the matrix multiplication of C, the matrix representation of the operator C is just the matrix representation of operator A times the matrix representation of operator B. Next, we will define the adjoint of operator O. If operator O operated on a cat vector A gives you cat vector B, then bra vector A operator operated on the bra vector A has to give you the bra vector B, or the adjoint of operator O operated on bra vector A has to give you bra vector B. So if O operated on cat A gives you cat B, that means bra C O cat A equals C bra C cat B. And similarly, if in the red on the right, if O adjoint operated on bra vector A gives you bra vector B, that means bra vector A O adjoint cat vector C equals bra vector B cat vector C. Notice how bra C cat B equals bra B cat C, but complex conjugated based on complex conjugate properties. Therefore, you would get COA equals AOC complex conjugated. If C and A are basis vectors, then JOI equals IO star J complex conjugated. Or I-O complex conjugate, I-O adjoint J equals J-O adjoint or J-O-I complex conjugated. That means the matrix representation of O or O adjoint IJ has to equal OJI complex conjugated. So that means that the matrix representation of O adjoint is just the adjoint of the matrix representation of O. And if a matrix is self-adjoint or Hermitian, then or O adjoint equals O. That means IOJ has to equal JOI complex conjugated. And note that this is very important for later topics in quantum chemistry. Or in general, AOB equals BOA complex conjugated, where B and A are not necessarily basis vectors.